So we're talking about this now. See this, I think we came to, so this is the question here. So let me refresh your memory. So we are given a system here. This is the system given to us. So which is x dot equals ax plus bu, and y equals cx plus du, right? So this is c, this is x, and d is 0. 0 times u. So d is 0. And c is this guy here. This guy is c. This is c, this is a. Okay, and this is b, right? This guy is b. Okay, then what we did is we found the inverse of this guy, which is this. Okay, then also what we did is we found the x. I think we found the x also. So we know the formula is, let me go here. This guy, let me write it down here. So our x is, so as you know, your x is si minus a prime, a inverse, and x0 plus bu. Okay. Then we have this guy here. This guy goes in here. Okay. Then you have x0. X0 is how? What is the x0? X0 is this guy here. Times this guy times x0 is 102 plus b is what is b? Help me here. B is 010, right? 01. Sorry, 001. Sorry. So then u is e to the negative t. So inverse u is inverse Laplace transform of e to the negative t. So what is the inverse Laplace transform of e to the negative t? 1 over s plus 1. Okay. Then what did you get here? This guy is 1 plus 0 times this 1, 0 plus 0 times this 0, 2 plus 1 over s plus 1. Okay. Then you have to multiply this guy here. You have to multiply this, which is this, right? Which is this, by this, which is this. Okay. So let me multiply here. 1, 0, 2 plus 1 over s plus 1. Oops. So this guy here. Let me erase this, right? We don't need this anymore. Okay. Now let's multiply this guy together. When you multiply, so we figured out x1 last time. So from here, what is the x1? This multiplied by, because remember your x is, this is now your x, right? This is your x, because when this guy multiplied by this guy gives me x. Okay, this guy multiplied by this guy here gives me x. That's why this is no longer this is x now. Okay, so this guy is x. X equals this. Now what is your, this is your x1, this is your x2, x3, like that. Now, what is your x1? We did it x last time. Your x1 is so this multiplied by 1, which is s squared plus 9s plus 26 multiplied by 1. Then this multiplied by 0, right? Which is 0. Then 1 multiplied by this plus 1 multiplied by 2 plus 1 over s plus 1. Then divided by whole thing divided by this guy here on the bottom here, whatever you have here. This is the determinant, right? S cubed plus 9s squared plus 26s plus 24. So we did this last time up to here. Now let's figure out x2. How do you find x2? So x2 you have to multiply this guy by this, right? Negative 24 by 1. So this guy multiplied by 0, which is 0, right? Then s multiplied by this plus s multiplied by 2 plus s plus 1. Okay. Then you have this guy again, okay? X cubed plus 9s squared plus 26s plus 24. This is your x2. Okay. Then similarly, what is your x3? So x3. So this multiplied by 1, which is negative 24s. Then this multiplied by 0, which is 0. Then s squared multiplied by plus s squared multiplied by 2 plus 1 over s plus 1. Then divide by this guy again, right? This guy also goes in here. Okay, so if you simplify this guy, these three, then you happen to see like this. So your x1 is this, x2 is this, x3 is this. You get it like this. Okay, now what is your, now what you need to find is you have to find y, right? We need to find y, that's your goal. How do you find y? Y is, if you remember, y equals cx plus du, that's your y. Okay, what is your x? This is your x. This 3 is x, so this is x. Then this c is this guy here. C is this guy. What is d? D is 0. That's why 0 times u. You don't have to write this down, right? So this is what we have here. So that's y. So let's then if you multiply this together, what do you get? 1 multiplied by x1, 1 multiplied by x2, 0 multiplied by x3 plus 0. Okay, that's what we have. Then basically you have to add this together, x1 and x2 together, meaning these two together. Let's add them together. Okay, if you add them together, then you'll get this. Okay, so you'll get this. Then you have to do the partial fraction, right? See, I have done partial fraction here. This guy, a, b, c. Then doing the partial fraction, you get a equals negative 13 over 2, b equals 19, c equals negative 23 over 3. This is what I have here. So this guy is negative 6.5, which is 13 over 2, and this is 19, and this is 23 over 2. Okay, so then you got finally your ys is this. This is your ys. Now you have to do the inverse Laplace transform, right? Inverse Laplace transform of y. If you do that,
I'm sorry, Professor. Why is ys equal to x1s plus x2s? I didn't get that.
oh, okay. So if you go back, remember we know the two equations, right? So if you remember the two equation we're familiar with is x dot equals ax plus bu. What is the output equation? We call it output equation, right? What is this guy? Cx plus du, right? So see, we have done this before, right? See, these are what I'm talking about. So this equation I'm talking about, okay? So here, these are the two equations. So x dot equals this, y equals this. Now your d is 0. That's why you are left with cx. This is your c. This is your x. Then you have to multiply. These are two matrices.
Oh, okay. Now I'm following. I'm sorry. I got it now. Thank you very much.
Yeah, no problem. So then you have to take the inverse Laplace transform of this guy, right? This is ys. Now you have to find yt. That's our final solution. Then if you do the inverse Laplace transform, you know what is the inverse Laplace transform of this guy. This is 1 over s plus 2, right? This is 1 over s plus 3. This is 1 over s plus 4. What is the inverse Laplace transform of this 1 over thing? 1 over s plus 2 is this, and negative 6.5 is negative 6.5. And 19 is this, and 1 over s plus 3 is this. And 11.5 is this, which is negative, right? There is negative sign. Then, and 1 over s plus 4 is this. This is the inverse Laplace transform. Okay, so far so good.
Yeah.
Okay, now what is the second part here? Now second part is find the eigenvalues and the system poles. That's the next thing we need to figure out. Okay, eigenvalue and the system. So how do you find the eigenvalue? Eigenvalue is this guy set to 0. What is this guy? This guy is this guy, right? Remember, this is so this guy is this is this guy, right? This guy on the bottom can be written as s plus 2, s plus 3, s plus 4. So this means determinant of s I minus a equal to determinant of s plus 2, s plus 3, and s plus 4. S plus 3 and s plus 4. So that should be 0. When you equal to 0, then the value of s you get are called eigenvalues. Okay, so when you set this to 0, when this set it to 0, what do you get? S equals negative 2. When you set it to 0, what do you get? S equals negative 3. When you set it to 0, what do you get? Negative 4, right? So these are the eigenvalues. Okay, so that's how you figure out the eigenvalues. So set the determinant is 0, and what is the value of s are the eigenvalues. Does it make sense? So, right? Any question before I move on to next?
So S1 is not the S plus 1 is not the per the determinant.
Yeah, because remember we had to multiply by this guy, right? This is the
Yeah.
determinant. This is the determinant, right? What we did is we multiply by this guy here. That's why we have this s plus 1.
Gotcha.
Okay, so this is the determinant from the previous, and extra, this is extra.
Gotcha.
That's why I wouldn't have to write it down, okay? So, good. Now, so this is another example, but I'm not going to go through it. So just, it's the same example, but it's simpler. It's instead of 3 by 3 matrix, we have 2 by 2 matrix here. Okay, it's the same process. So we are going to find the yt again. It's the same way. Then we are going to find the eigenvalue in this way, and which are negative 2. And so this is the same thing. You can go through it, but I'm not going to go through it now. Now the next one, this is the last one of this topic. Then, so underdamped second order system. Remember, we have different kinds of system, right? We deal with different kinds of system. So what are they? Undamped, underdamped, critically damped, and overdamped, right? Now we're going to talk about, in particular, we are going to talk about underdamped. We are more interested in this kind of system because there are lots of system in physics or physical science that are underdamped. Okay, so instead of going through everything, we just go through underdamped system, underdamped second order system, which is, as I say, a common model for the physical problem. Okay, so as we know already, so we already, in the case of second order system, what are the parameters we talked about? We already talked about zeta. By the way, this guy, remember I forgot the name last time. This is called zeta, and this is omega n, which is natural frequency, right? So we talked about these two parameters already in the previous lectures. Now, when we talk about underdamped only, then we can add these parameters also. These are specific to underdamped system. Okay. Besides these two, in addition to this, right, you have these parameters that are used to define the transient response of the system. Okay. So what are they? The specifications are peak time, TP, rise time, TR, percentage overshoot, which is written as this, percentage OS, then settling time, right? So these are the four more. In addition to these two, we have four more parameters that we can use to characterize this kind of underdamped second order system. So let's define them one at a time, one by one, okay? So what is peak time? TP, right? As you know, in the previous lecture, RG for the second order system is this, right? This is RG for the second order, any second order system. But now we are talking about underdamped. Since we are talking about underdamped, so our system will have zeta is smaller than 1, right? Okay, our zeta will be smaller than 1, like this. So this is what we are talking about now. Now, if this is your C with zeta less than 1, right? So you are interested in CT, right? Ultimately, not CS. So after doing some inverse Laplace transform, this is a little bit involving here. The math is a little involving. We are not going to do the math right here. I'm just giving you the final answer. So if CS is this, okay, with zeta less than 1, because this is underdamped system, then after doing some math, we get CT equals this guy here. Oops. Okay, your CT equals this guy. That's what you get. So what is this guy here? Let's see. We have 1 minus 1 over 1 minus zeta square root e to the negative zeta omega n t. Then cosine this factor. So you have phi here also, where phi is defined as inverse tangent of zeta over this guy. Okay. Basically, this is your CT, where phi is defined like this. Okay. That's your CT. Now, if you want to consider underdamped, what happens? Sorry, not the peak time. If you want to define peak time, how do you do? Peak time. So what you do is you take the, okay, what is the peak time? First of all, let's define the peak time, then I'll give you the formula. Okay, what is the peak time? Peak time is the time to reach the first peak, because we have a signal like this, right? Like this. This is your first or maximum peak. Over time, it decays, right? This peak is smaller than the first one, and we have another peak here. Maybe this is smaller than the second one, and so on and so forth. It decays. So this is the first peak. What is the time for the first peak? That time is called TP. Okay. So if you use this formula again, this is the formula we talked about. If you use this formula and take the dct derivative, right? Take the derivative. with respect to time and set it to 0. Remember, this is how you find maximum minimum, right? Take the derivative of this function and set it to 0. If you do that, I'm not going to do that. If you do that, finally you get TP equals this. This the time for this peak, okay? For this peak, what is the time? This time, okay? This time is this guy. Okay, then what is the percentage overshoot? Percentage overshoot is defined by C max minus CSS divided by CSS. What is CSS? Suppose you have this, right? So this is your steady state value. After some time, it becomes steady, right? This is steady state value, SS, or we can call final value. Okay, and this is the Cmax. So this Cmax minus this value, okay, that's on the top. Cmax minus CSS divided by CSS, again the same CSS, then expressed in percentage, which is called percentage overshoot. Okay, that's called percentage overshoot. So if you use the same previous CT, right? Remember we had this equation here, this guy. So from this equation, if you do that, then you'll get percentage overshoot equals this here. That's the formula you will get for the percentage overshoot. Okay, so if you invert it, right, then you get zeta equals this guy here in terms of percentage overshoot. Okay, you just invert it, right? This is percentage overshoot in terms of zeta. This is zeta in terms of percentage overshoot. Just invert. Okay, that's what you get. Then next one is settling time. Settling time is defined that it's like the same as in these two guys are same as in first order. Remember we already did these two. Okay, these are same as in first order system. What is your settling time? TS is defined as the time for response to reach and stay within certain percentage of the final or steady state value. Suppose, so it reaches, so this is your 98%, this is your 100%, right? So between 98 and 100. Okay, so right here, this time is called settling time. That's called 2% settling time, okay? But you could have 5% also, meaning this is 95. You know, it will be little down here, right? Maybe this is 95. So this is now, which is 5% settling time, which is equal to 3 tau, and 2% settling time is equal to 4 tau. That's what you get, okay? Well, I'm not going to derive it, just for your information. Yeah, similarly, we have the rise time as in the previous first order system, right? We did that in first order system. In the same way, we have the rise time, which is define the time for the waveform to go from 0.1 to 0.9 of final value, okay? So I can show you all those things here. So this is your 0.1 to 0.9. Okay, this time is the rise time. Similarly, this is the TP, right? Maximum, see that? This is maximum. Okay, so this is, maybe this is, this value is 98%, right? See, this guy is 98%. So this is TS, settling time, 2% settling time. Okay, that's how it works. Now let's do one problem, then I'm done with this chapter. For the transfer function below, find the peak time, percentage overshoot, and settling time. Okay, so we have, this is my equation, right? Second order equation. But what do you have here in your case? You have this here. So how do you compare these guys? First of all, let's find omega n. What is your omega n? See, omega n squared equals 25. So omega n squared is 25. What is your omega n? Omega n is 5. You don't have to write plus minus because frequency is a number, right? So you don't, number of cycle per second. So that's why you simply write 5 hertz, right? That's your omega n. Done. Omega n is done. Now, so now next now based on, now what do you need to find next one? So omega n is done. So how do you find this zeta? So 2 zeta omega n s equals 5s, right? Then what is your omega n? Omega n is 5. What is your s? S is s, right? 5s. So actually you can cancel this each other, right? Cancel out, right? Then you have 2 zeta 5 equals 5. 2 or 10, right? 10 zeta equals 5. What is your zeta? 5 over 10, which is 0.5. So what kind of system is this? Help me here. Underdamped, overdamped, underdamped, right? If it is zeta less than 1, this is underdamped system. Underdamped system, right? Now, after you know zeta and omega, can you figure out TP? That's your goal, right? And the peak time. TP. What is the formula? As we derived earlier, this is your formula. Just plug in the value of omega, which is 5, right? Omega is 5 and zeta equals 0.5. Just omega is here, which is 5. This is 0.5. Then pi is, you know the value of pi, 3.14. So then you get this much. If you calculate this, you'll get this. Then similarly, percentage overshoot. This is the formula we had before, right, in the previous slide. So this is the formula for percentage overshoot. So zeta is given, then just plug in the formula value and multiply by 100. This gives you percentage overshoot. This guy is done. Then similarly, settling time. How do you find settling time? Is 4 times tau, right? Okay. So we know tau is this. Tau is 1 over this guy. That's why 4 times tau equals 4 divided by omega n. So you know the value of zeta and omega n, just plug in and you get this one. This is how you figure out those parameters. Question here. So guys, now that we have done with chapter 4, now we'll have the midterm next week, okay? Just I'll talk about that later in the before the end of the class today. So your midterm will be from 1 through 4, chapter 1 through 4. So we'll have it next week. All right. So let's talk about chapter 5. So reduction of multiple subsystems. Guys, do you guys have any question about midterm?
Not really. Would it be a study? Oh, sorry. Would it be like a study guide or just homework?
Yeah, if you want, I can put the study guide too. But
if we can just do the homework and it'll be, then I'll be fine. Then that's fine by me.
So which day you want to take next week? Let's finalize then. So we have to reduce your multiple system to so-called equivalent system. Okay. All right. This is the goal in this. This is what we do in the chapter 5. Okay. So when you talk about multiple subsystems, we can represent in 2 ways. As we see earlier in the previous chapter, we use block diagram, right? We use block diagram. What is the stuff that we use for the block diagram? We use the integration block, right? Remember? Then we use the summation block. Then we use the scaling block, right? Stuff like that. We use the block diagram. Now, this is one of the methods used in the reduction of multiple subsystems. And there is another method which is new to us, is signal flow graph. Okay, so either you can use this representation or you can use this representation. Okay, so either or. Okay, so let's talk about when you talk about multiple subsystem and a block diagram, because last time we talked about block diagram in a single system, right? For one subsystem, I would say one subsystem. So far we have been doing this, one subsystem. Now, since we will be doing many subsystems and reduced to equivalent, right? Many subsystems reduced to equivalent. So in this case, we need a couple of more blocks, not only summation block, summing junction, you know, scaling block. We need a couple of more blocks. Okay, so one is summing junction. I think we already did that, summing junction, where output signal is algebraic sum of input signal. Okay, this is the summing junction. In the summing junction, we add all those things, R1, R2, R3, then you get the output, which is R1 plus R2 minus R3 in my case, because my R1 is plus, as you can see, R2 is plus, but R3 is minus. Okay, that's what we have here, plus, plus, and minus. Okay, that's the summing junction. Similarly, another block we need is pickup point. Okay, so another point is pickup point. What is pickup point? A pickup point distributes the input signal undiminished. See, this is very beautiful, undiminished. So suppose this is your RS and this is the pickup point, then your pickup point will give RS here, exactly same RS here, exactly same RS here, and exactly same RS here. So this point is called pickup point. Okay, so we need two more concepts here if you want to do the block diagram of the multiple system. Then finally, we'll reduce to equivalent system. Okay, all right, so there are four forms of a block diagram. Block diagram are of four kinds. One, the cascade, means series, meaning you have the block 1 here, block 2 here, block 3 here. If you add them in series like this, right, they are in series, right, you can clearly see they are in series. This is RS, then what should be the output here? Help me, if this is RS and this is GS, what is the output? GSRS, right? And I simply call it X2 for that. Then similarly, this X2 is my input now, G2. Then what is the output? Output is X1, which is G2 times these two guys, G2, G1, RS. Okay, G2, G1, RS. Now this is the input to this system. Again, then your output will be G3 times these three guys, G3, G2, G1, RS. Then what do you see? If you represent this whole thing, one system, right? Let's say this is the one system now. Then what do you get? You can say this is RS, this is my CS, where CS is this multiplied by RS, right? So this is the G, the equivalent transfer function. So the conclusion is, if you have blocks in series, then equivalent transfer function is this. It's like the register series and register in series and register in parallel, right? It's like that. So if the transfer function in series, G1, G2, G3 in series, then equivalent will be RS equivalent will be G equals G3, G2, G1 in this order. Now what is the parallel? Parallel is if you have G1, G2, and G3, the parallel will be, so this is what it means. So you have RS here, RS goes here, RS goes here, RS goes here, right? Then they add up. Okay, if it is, so it could be plus or minus, right? When they add up, it could be plus and minus. Similarly, this guy could be plus and minus, this guy could be plus and minus. Okay, then if they are connected in series, your CS will be plus minus Z1 plus minus Z2 plus minus Z3. Suppose this is plus, this is plus, this is minus, then your CS will be G1 minus, sorry, G1 plus G2 minus Z3. Okay, plus, plus, minus, plus, plus, minus. So conclusion, if you have series, they multiplied like this. If you are in parallel, they added together like this. That's the conclusion, okay? Now next one is feedback form, okay? Feedback form. So meaning, so you have, so I'll take you guys to the chapter 1 now. If you remember, we talked about feedback in chapter 1 also. Okay, we talked about this kind of circuit there, if you remember. But I'll refresh it, don't worry. So now you have the input here. You have the input here. Then this is summing junction, right? You have plus, and then this is the summing junction. Then you get the ES. Okay, so this is the controller defined by G. Then you get the output, right? Then from output is connected to input again. Now you have this another transfer function. In this case, this is related to feedback loop. That's why we don't call it G. It's the transfer function, but it's in the feedback loop. That's why we call it H instead of G. Okay, so then this is connected to the summing junction. So here, now suppose this is minus, then what is the entire how do you represent this guy? So this is what I mean. So how do you represent this guy here now? What is the equivalent of this guy? CS is there, RS is there. Okay, RS is there, CS is there. What is the equivalent of this guy? This guy will be written like this. So if it is minus, then you will write GS over 1 plus, see, GS means this guy, over, this guy over, then what do you have here? 1, then plus, then multiply this together, GS, HS. Okay, if it is minus, you get plus here. If you have plus here, then you get minus here, okay? That's why I said this minus plus becomes plus minus here. So if it is minus, then the system is called negative feedback. If it is plus, then it is positive feedback. Does it make sense so far? Now, number 4, okay, this should be number 4. Now, in this case, what we talk about is we have different forms of circuit here. So let's say this is your given circuit. For some reason, you want to rearrange this guy, rearrange. So how can you rearrange this guy? You can move this GS to the left of the summing junction, right? This is the summing junction. So this GS is on the right, right? You want to move it here for some reason, okay? Then how do you move it? If you want to move this guy here on the left, so look at that. So RS is here, then you move this here, right? To the left of summing junction here. So that's what we have here. Then what you do is, you have plus minus, this thing is same. We don't have any change here. This guy is same thing. Then if you move this guy here, then you also have to move this guy here. Like this. See, you have two GS here. So then your X goes through GS and goes to the summing junction. Okay? So these two systems are exactly the same. So these systems are exactly the same. Guys, question here.
No, can you remind me why one of our arrows has a plus on it, the other one only has a plus minus on it? Is that just given?
Oh, here?
Yeah.
Oh, yeah, because on your RS is already added to the system, right? But the thing is, in the negative, this is the feedback loop. You know, this is the feedback loop. It comes from here, right?
Gotcha. And that can be plus or minus.
Yeah.
Okay, gotcha.
Yeah. So similarly, if you want to move the block to the right of the summing junction, right? Suppose you have this, you started with, let's say you started with this, right? So in this case, your GS is on the right. In this case, your GS is to the left of the summing junction, okay? If you start with this, how do you represent this guy in another way, in different form? In different form, so if you want to move this to the right, then what you do is, see, I just moved it to the right. This guy is now to the right. See, this is the guy here. So when you move to the right, not only you do this right here, you have to also put this here. But it comes as 1 over GS then, in this case. Okay? That makes sense, right? Because you are getting XS here, right? This has to go XS. Okay, XS has to go here, like this. But here, if you move this guy here, then your XS has to move through GS also, right? Which is not desirable, right? Which is not desirable. That's why you have to have 1 over GS. So these two cancel each other, then you are getting XS again. That makes sense, right? So RS, see, RS passes through GS. That's okay. RS passes through GS. But this XS does not pass through GS. That's why if you have here, then you have to have 1 over G. So that 1 over G and this G cancel each other. Does it make sense? Okay, similarly, for the pickup point, so how do you do the pickup equivalent for, so we're talking about pickup point now. This is the pickup point, right? So if you have this kind of circuit associated with the pickup point, this is pickup point, right? Pick-off point. So this is pickup point. Now you have G in one of the branches of the pickup point here. Then how do you represent this guy? Is there another way of representing this guy? If you want to represent, meaning if you want to move to left of pickup point, if you want to move this GS here, which is left of the pickup point, right? This is pickup point. So if you want to move this here like this, then what do? Then you have to do 1 over GS here, because this signal does not have any GS involved, right? So since you have GS here, so you have to cancel that effect. So that's why you have to do 1 over GS here. Similarly, you have to do 1 over GS here. Make sense? So similarly, if we started with this, where GS is on the left of pickup point, right? This is a pickup point, you have GS on the left hand side. Then if you want to move this GS to the right hand side of this pickup point, here, here, and here, like this, right? Three GS's. Then what do? You have to multiply GS on each branch, like this, right? Here, each branch you have to multiply by GS. So they are exactly the same. Similarly, they are exactly the same. Question here. Please, question here, please. So far, so good.
Yeah.
Okay, nice. Now let's do the other one. Let's do one example here. So we talked about reducing in the the different system into one equivalent system, right? So depending on, based on the techniques we learned so far, let's simplify this guy here. This is the circuit given to you. Can you simplify this guy like this? RS and C. So instead of having all those things, so reduce this to single block here like this. How can you do that? Okay, let's learn that here. So first of all, let me start with here. So you have R here, you have the summing junction here, you have the summing junction here, you have G1, G4. Let's use the series rule, right? So how do you add these two guys together? Series, right? That is series. So this is what I'm doing here. First step is I'm trying to condense these two guys. How do I condense them? If they are in series, you just multiply, right? See, you have G1, G4. So this guy is now G1, G4. This guy is now G1, G4. Done. This is simplified. Now, so how about this guy? Let's simplify this guy here. How do you simplify this guy? So these two are in parallel, right? Okay. So these two are in parallel. That's why simply this one here. So this one parallel. Yeah, this guy. That's why you have G1 plus G2. So this guy is done. This guy is done. This is done. Now let's simplify this guy now. This chunk now. How do you simplify this chunk? You have G1, G4 already, right? This guy is already G1, G4, G1, G4. Now G1, G4 and H, they are in parallel, right? Okay, what do you do? G1, G4 and H, they are in parallel. Then what do you do? G1, G4, then it is plus or minus, this guy. This is plus, right? They should have minus here. G1, G4 divided by 1 minus G1, G4, H1. 1 minus G1, G4, H1. So this guy is done. Now let's see. You have R here. I have this guy here. This guy is this guy exactly, which is instead this, right? They are same. Then you have this guy here. This is this guy, right? See, these are coming from here to here. Then you have H2 remaining, right? That's the last thing we are left with. So then you have H2 there. So what do you do here? So what you do here is you have these two in series. These two in series, these two are in parallel. So meaning you multiply this together. So meaning this guy multiply with G1, G4. Oops, sorry. G1, this guy multiply with G1, G4. Okay, they are in series. They multiply. Then now this combination is in parallel, right? So that's why. So G1, G4 divided by 1 minus or plus here. See, this is minus, right? See that? When you have minus, you'll have you'll have plus here, right? See that? That's the thing. This minus gives you this plus. So then you have again the same thing here, right? In H2. So that's how you simplify your entire system to condensed equivalent system. This is condensed question here. So let's do one more.
Sorry, Professor. Could you go back for just a second?
Okay.
Thank you.
All right. So now so far we did the block, right? So what is the next one now? So block diagram method, right? So remember we did two methods here. We said there are two methods. One is block diagram methods, another one is signal flow method, right? So this is completely new to us. This is completely new. So let's do signal flow graph now. Okay, you can choose either or. Okay, in the signal flow graph, which is alternative to the block diagram, right? As we said earlier. So first of all, let's see what are the components in the signal flow graph. So you have branch and nodes, okay? Branch and nodes. So signal flow graph consists of branches and nodes. A branch is same thing as transfer function. Remember in the transfer function we had a block. This is R, this is C. This is block, right? This is G, right? Okay. Now this G is simply represented by branch here, like this. This becomes branch. And the node represents the signal. Okay, this is signal. Now you have node here. This is also signal. You have node here. So, in other words, so if you have this kind of system in the block diagram, right? In the block diagram notation, then this can be represented in the signal flow graph like this. So this RS is line here, right? This is line. Line becomes node. See, this line is simply a node. This entire line, this line is node right here. And this block is line now. See, that's the block from here to here. Your block is now line from here to here. Then you have a line here for the signal, and that becomes circle now again, node, which we call node, okay? So you can represent one way or the other. So this representation or this, they're equally valid. So let's do some of the conversion between block and signal flow graph, okay? Suppose in the case of block diagram, we have cascade form of this system, right? You have RS goes through G1, then G2 and G3, right? And how do you represent in signal flow? So this becomes a node, okay? And this becomes another node. This becomes another node. And this becomes another node. Okay? So this is CS, which is CS. This is X2. This is X2. This is X1. This is X1. This is RS. This is RS, right? Then how about the blocks now? This block is simply a line. This guy is a line here. And you have an arrow, right? And I call it G1. This is G1. Then you have another block, which is a line with arrow, and it is G2. Then another block G3, line with arrow, G3. That's how you represent in the signal flow graph. Then similarly parallel, right? So suppose you have parallel here. In the block, you have this kind of circuit, right? You have R, you have G1, G2, G3, and they meet up right here. And this is the output. Then how do you do that in the case of signal flow graph? How do you do in the case of signal flow? So this is how you do it. Let's see. This line becomes node, right? Then you have G1, right? You have G1, G2, G3. They are line, right? Remember? They are line. This is G1. This is G2. This is G3 with arrow on it. So these are these three guys here. Then you have the signal X1, right? Signal is X1. This is X1 signal. This is X2 signal. This is X2 signal. Then X3 signal. This is X3 signal. Then these three meet up at the junction and gives you C, right? This is your C. So that's why. So this is the meetup. At this junction, they meet up and give you C. So they meet up here and give C. But how about from here to here? What do? There's nothing in between, right? Remember here you have Z1, but you don't have anything here. So there is nothing. That's why you have to put 1. Your transfer function is 1 here. If there is nothing, that's why 1, 1, 1. Right? Makes sense. The similar feedback form. So if you have this kind of in the feedback form, the block diagram, then how do you represent in the signal flow graph? So this guy R, right? This signal is line here, becomes a node. Okay, then you have the same R. Actually, yeah, the same R goes here and meet up E, right? So this is so. Okay, let's do this. So you can say, okay, this is R, right? This is R. This is R. This is R. So this G, let's talk about this G. This G is this here, right? Then this C is circle, right? Or node. Then you have H, which is negative, right? That's why you have negative H coming to the E. So how do you connect E and R then? E is a signal, R is a signal, right? So is there any G in between? No, that's why you put 1 there. Does it make sense? Guys, question here, please. So far, so good. All right, let's do the similarity transformation. So as you know, state space representation is unique, right? State space representation is not unique. So there is one set of representation and there is another set of, this is set 1, this is set 2. So how do you know they are similar? Okay, we can make some kind of transformation, which we call similarity transformation. So using that transformation, we can change one set to the another set, okay? That's called similarity transformation. So let's begin with our well-known system. So we have x dot equals ax plus bu. Your y equals cs plus du. What is your x? X could be a vector having n components. This is a state vector, as you know. Now I want to change this system. This is set 1. This is my set 1. Now I want to find exactly similar another set 2. So from set 1 to set 2, I go through a route called similarity transformation. Similarity transformation. Okay. So for that, to understand this, let me write x equals pg. To understand this route, let me write x equals pg. This x is pg. P is a matrix. Any matrix that is unknown right now. Okay. But that P is a transformation. That P is will be called transformation matrix. Okay. So this X is vector having n component. That's why that P has to be score matrix having n by n. Okay, this P has n by n elements because your state vector is, has n component, 1 through n, right? See, 1 through n. That's why your P has n by n. There is no doubt. Okay. Then what happens if you take the derivative of this guy? X dot equals P is constant, right? So G dot, right? You got that? Then let's plug in the value of Z dot here. So let's see. X dot equals, so X dot is this guy. Then AX, what is your AX? AX becomes AX is PG, right? Okay, that's what I meant. Then BU is BU. BU is BU. And how about this guy? Y is Y, right? C is C, X is PG again. PG again. And DU. Okay? I just plugged in. X equals PG. Then pre-multiply this guy by inverse of P. What do you get? If you pre-multiply this guy by inverse of P, what do you get? So if you do that, what do you get? This guy is G dot, right? Because this guy is 1. So G dot here on the left. Then what do you have here? Help me. P inverse AP G, then P inverse BU. Now I want to match the form here. So you have Z dot equals X dot equals AX plus BU. Similarly, Z dot equals ASG plus BSU. So this BS, sorry, this B is BS here. This U is U. Okay, they're same. They're similar. Not same, they're similar. Similarly, this X becomes G and your A becomes AS. Okay, then G X dot becomes Z dot. So now, similarly, how do you get the Y? So this guy here. So this Y is C, right? C times X is PG again, right? See, X is PG, X is PG. Then DU is DU. Then this can be written as C times this is, sorry, this is CS, right? This is CS, and this is G. Okay. Now this C is similar to CS, X is similar to G, D is DS, and U is U. Now you have two sets of representation. Now, what is your AS? AS is this, right? Remember, AS is this. Then BS is this, right? And CS is this guy here, CP. Then DS is exactly D. Okay, there is no change. There is no change in D. If you do that, okay, then they look similar. See, this is in terms of G dot. This is in terms of, this is X dot. This is G dot. This is similar to that guy, and this guy is similar to this guy. So okay, so this guy is similar to these two guys here, and these two guys is similar to these two guys. Okay, this is set 1, this is called set 1, this is called set 2. So you can go from set 1 to set 2 by using the similarity transformation, where AS, BS, CS, and GS are defined by this. This kind of transformation is called similarity transformation. Make sense? Let's define the, now we have the two system, right? We have system 1, okay? This is system 1 or set 1. This is system 2 or set 2. How do you define the transfer function here? In this case, that's how you define the transfer function, right? Remember, this is the formula from previous chapter. So this is the formula for the transfer function in this kind of system. Then similarly, what is the transfer function for this kind of system? Your C becomes CS now, right? For this system, your C becomes CS, SI is SI, then A becomes AS, B becomes BS, and D becomes DS, right? Now, you have two transfer functions. One from this set, which is this. Another transfer function from this set, which is this. Okay? Are they similar? If they're similar, this transfer function should be exactly equal to this one. Okay? So how do you know that this set is similar to this set? This set is equal to this set, or similar to rather, if the transfer function is exactly the same. Does it make sense? Let's find one similarity transformation, then done for the day. Guys, so far so good. Lucas? Emery?
I think so.
Okay. Okay. Everybody else? So far so good, right? Let's do one problem, then we'll done. We'll be done. So now in this case, what is your A? This is your A. This is your A. This is your B, right? This is your C. Now find AS, BS, and CS because there is no D here. You don't have to worry about D. Okay. So now I'll define the new system. Okay, this is given. Up to here is given. Everything else is given. This is given. You are given this system, and I'm asking you define your G1 as 2x1, G2 as 3x1 plus 2x2, G3 as this. I'll ask you to define this way. Now I'm asking you to find the similarity transformation in this notation, in this state vector, state variable rather. In this G1, G2, G3, what is the similarity transformation? Okay. So what is your, how do you find your G? In the previous slide, how do you find the G? Remember your X is PG, right? And what is your G then? If you pre-multiply by this, what do you get? You got G, right? So G equals, okay, that's what it is. So now what is your G? So then what is your P? So can you find P from here? Let's write this in the matrix form. So how can I write this in the matrix form? G1, G2, G3 on the left, right? Then what do you have on the right? Help me here. Then you have X1, X2, X3.
Just a quick question, Professor. What you wrote up at the top right-hand corner, that x equals pz and whatnot, is that always the case?
Yes.
It's always the case. Okay,
Yes.
thank you.
Yeah, so this is what we did here. See here, we let x equals pg. Okay, it's always the case. Yep. So then what is your G1 here? G1 is 2 times x1, right? 2, 0, 0. These two are 0. Then what is your G2? 3, 2. 3, 2, 0. Then what is this guy? 1, 4, 3. 1, 4, sorry, 5. So this is my P. P inverse, sorry. This is my P inverse. So this is G. This is P inverse. And this is X. So that's my P inverse. I got P inverse. So what do you need to find now? You need to find, once you have P inverse, what do you need to find? AS equals P inverse AP, right? So how do you find, now you have P inverse, find the P. How do you find P? Remember, if you find the P, P is P inverse of inverse, meaning find the inverse of this guy. Find the inverse of this guy. That's the P. So you find P, then multiply by A. This guy is A. Then P inverse is given if you can find AS. Similarly, you have to find BS, right? How do you find BS? P inverse B. This is your B, multiply by P inverse, which is this guy. That's how you find BS. Similarly, CS. CS is C times P. This is C. Here you will find P, right? C. Then do the P times C gives you CL. So that's how you do it. If you do that, you'll get all these things. C, this guy, this guy. Okay, then finally you get this. All right, guys, this is it for today. You want to do this at home? Just try this one. Try to find, this is just a matrix algebra, okay? So find the, your, if P inverse is given like this is given, then P will be this, okay? So P will be P inverse, like that.
Have a nice day, Professor.